Lab 4 for a magnetic field of a bar magnet. So to begin, the purpose of this lab was to determine the magnetic field of a permanent dipole magnet by experimentation and mathematical modeling. I applied principles of magnetism, including magnetic field and magnetic force, as well as superposition and Biot-Savart law. For the procedure of finding the distance dependence of the magnetic field, we determined the magnetic field of a permanent dipole magnet by using the magnometer of a cell phone, which we measured using the Firefox iOS app to measure the magnetic field of my bar magnet. I compensated for magnetic north of the Earth's magnetic field by aligning my phone so that the X component read as close to 0 as possible. I found the location of the magnometer chip in my phone by aligning the east and west and north and south axes of the phone until the appropriate X and Y values were maximized or minimized, and then found the location of the phone magnometer chip to be about where the X is. I then measured the magnetic field at a horizontal distances r away from the magnet for 5 values of the magnitude of the X component of the magnetic field, where the X component was 20, 70, 120, 170, and 220 microteslas. The procedure for finding the off-axis field of the magnet followed as, after measuring the distance dependence of the magnetic field, I measured the off-axis field. I first found the distance d perpendicular, where the net magnetic field was about 100 microteslas. Then, with the positioning shown in the diagram, I measured the x, y, and z components of the net field at a distance d from the magnet. Then the y component of magnetic field was corrected to account for the Earth's magnetic field by subtracting by of the Earth from by at the radius r equals d. Then we repeated the trial 3 times to get an average value for d perpendicular and b net. Here's a look at the experimental results for distance dependence. I measured the distance and the x component of the magnetic field and repeated the trial 3 times and calculated the average, and these same measurements are repeated for all 5 distances to get average distances and average x components of the magnetic field. Then the natural log of both were taken to plot a linear graph, which is shown on the next slide. In general, observations included that as the magnometer moved closer to the magnet, the measured x component of the magnetic field increases, and this can be seen as here the radius decreased, the phone was moved closer to the magnet, and the magnetic field increased. And then when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As we got farther away, the radius was larger, the x component of the magnetic field decreased and would have eventually reached 0 the farther we had pulled the magnet away from the phone. Then here's the graph of the results. The natural log of both sides produces a linear result with an equation y equals negative 2.935x minus 14.34. 14.34, negative 14.34 is our y-intercept, and we use this y-intercept value to calculate mu, the magnetic dipole moment. And through the calculations seen right here, we calculated mu to be 2.959, which is very close to our expected value because the theoretical equation, has an n value of 3. Then here's a look at the results from the off-axis field. I measured an average d perpendicular of 2.02, which translates to a distance of 0.202 and 0.285 meters. And at this perpendicular distance, I found a magnetic field of negative 4.8, negative 1.14, negative 4.14 teslas, all to these values would have been in microteslas. But yeah, magnetic field as shown. Then to simulate this situation in GlowScript, I calculated the magnetic field of a dipole using the formula right here. And here is the function in GlowScript that I used, calculating the magnetic field. And then at several observation locations, we called the function to calculate this magnetic field on the axis in 2 positions and then on 4 perpendicular axes. And then here shows how I calculated the magnetic field 45 degrees from the axis, which is how we simulated the off-axis field in the actual experiment. And this is a look at the glow script model. The blue arrows are the B field on axis. The orange arrows are the perpendicular B field. And then at a distance of d equals 0.285 meters, our glow script model found a magnetic field similar to the experimental magnetic field, except a zero component in the zero for the z component, which is different from our experimental results. Assumptions made in this experiment include that we assumed the bar magnet acted as a dipole and that there was no contribution from the Earth's magnetic field by aligning the magnet with magnetic north. And the magnitude of the magnetic field we assumed to decrease as distance increases, showing the distance dependence of magnetic field. Potential errors include additional metal impacting the magnetic field, such as screws in the floor, nearby metal table, electronic devices. It was very difficult to find a location where there was minimal other magnetic influences. The location of the magnometer in the phone could have been off, and the phone could have not been pointing exactly north, which could have skewed the results due to the Earth's field. These what-if questions kind of address some of the assumptions. What if you hadn't oriented your experiment to compensate for magnetic north? The Earth's magnetic field would have skewed the results, and yeah. What if you were to stick two identical magnets together end to end and run the experiment again? The parallel placement of these magnets would have an additive effect, and so the strength of the magnetic field would increase overall. I would expect my measurements to be larger. And that's all. Thank you.